All right, so now we're going to introduce, or actually just talk about, because I think you already have heard of what a titration is, right?
Yeah, we did titrations in, did we do them in 105 and 106 lab?
Yeah, we did. We did them in both 105 and 106 lab. Now, some of you weren't, well, yeah, I think all of you, well, maybe a couple of you haven't taken 106 lab yet, but in 105 we also did a titration. Let's see if we can remember the titration that we did in 105. Do you remember what we did?
Nope.
Well, we used methyl orange and phenolphthalein. Do you remember that?
Oh, yeah, I do remember that. Let's see, so what did we have there as far as methyl orange and phenolphthalein?
Well, what we did is we had some sodium bicarbonate, right? And we had some HCl, a solution of HCl. Okay? Now, the solution of HCl, we didn't know its concentration. All right? And we also, I mean, this was just a bottle of sodium carbonate. Did I call that sodium bicarbonate? It's sodium carbonate. This is just a bottle of sodium carbonate. And the first part of the lab was to identify the concentration of the HCl using sodium carbonate. Sodium carbonate is a good standard, all right? Do you remember the parameters that makes the characteristics of a good standard?
So a good standard is something that you make a solution of and its concentration is not going to change.
Okay, that's good. Not very hygroscopic, meaning it's not going to absorb water from the surroundings very well, right? I mean, it does, but the timing of it takes a significant amount of time. So if you weigh out an amount of this material, you can be pretty confident that that's the amount of material that you have in your mass, and not a significant component of it is water. All right? You dissolve it in water, and it will stay there in water. Now, it's true, the carbonate, some of it might become bicarbonate, but if you perform a titration, and in this we were combining these two, so what would the products be if we combined HCl and sodium carbonate?
Let's see, I guess we'd have sodium chloride.
Very good. And what else?
H2CO3.
Very good. And I like the way that you make sure you had two H's on that CO3, right? We have to remember that's a 2- ion, therefore we have two hydrogens, right? Okay, now H2CO3 also was an important compound. Well, we'll just leave it at that for now. But if we wanted to have this balanced, we noticed that there was 2 HCl's necessary for every sodium carbonate. Do you remember that part?
Oh, less so, but okay.
All right. And then what we said was that we reminded people, or we introduced at the time, that a chemical reaction like this, if it's performed in the form of a titration, where we have, so to start off, I had a flask here which had a little bit of sodium carbonate in water. Okay? So I had a solution of sodium carbonate in water. And then I had a Buret, right? And in the Buret, I had my HCl. Okay, do you remember this?
Yeah, I think so.
What else did we have? Or what else do we need? What's a titration? Do you have a good definition for a titration by chance?
No, I don't really do.
All right, so a titration is an experiment in which we have a known, and initially this is our unknown, and we have a chemical reaction between them. So we need to know the stoichiometry here, right? That's very helpful, at least. There's some stuff you can learn if you don't have it, but... And then we also need a way to tell that the titration has come to a finish, or that this reaction has come to completion. All right? And that we call an indicator. All right? So something's going to tell us that the reaction has finished.
That was the methyl orange, right?
Methyl orange. And then there was also, we also had a container of another, so this one's methyl orange. We also had another indicator, a dye that changed color for us, which was called phenolphthalein, which I'll put in PHEN, okay? So I had methyl orange and phenolphthalein. and we were introducing the fact that this reaction, when you start off with the sodium carbonate and you gradually add the HCl, so we're not adding 2 moles of HCl all at once, we're gradually adding the HCl. Well, what happens is the HCl interacts with the sodium carbonate, any HCl we add, and the product is one of these sodium chlorides and an HCO3 minus ion, or bicarbonate. And this process will continue until let's see, what are we missing here? To kind of balance the equation, I guess we would have to say that we have a sodium ion in solution. So this will continue until all of our sodium carbonate is converted to the bicarbonate ion, right? If this were an ionic equation, it would have 2 sodium ions, a carbonate ion, a hydrogen ion, and a chloride ion, and this would be ionized as well because it's a soluble ionic compound, HCO3 minus and the sodium ion. And then if we look at the net ionic equation, we have these 2 sodium ions gone. The chloride ion is also gone. So what's happening is we're adding acid, the H plus component there, to a carbonate ion, and carbonate ion, and we're making the HCO3 minus ion, the bicarbonate ion. So this is occurring every time a little bit of acid is added. The sodium carbonate is taking up that acid and making it bicarbonate. And that will continue little by little until all of the carbonate is consumed and the bicarbonate is the only thing left over. All right? Once the bicarbonate is all that's left, all the carbonate has been consumed, right? This HCO3 minus can take another proton and form H2CO3, right? Carbonic acid. But it won't do that until all CO3 minus species have a hydrogen ion already, okay? So, and it also won't take a second carbonate ion until the hydrogen ion concentration has reached a certain threshold, okay? So let's think about this more molecularly, okay? Let me draw a picture of this equation here in a kind of a molecular image of what's going on here. So I have the hydrogen ion, which I'll just write as H+, and I have this thing, CO3, with 2 negative charges on it, right? There's a certain affinity for hydrogen ions by these oxygens, or by this whole molecule in general, okay? That means that when hydrogen ion comes close, this carbonate will draw it in and hold on to that hydrogen because of that negative charge, all right? After you get that hydrogen ion on that oxygen, the affinity for a second hydrogen decreases, all right? And so that first hydrogen ion will only go on here, and then the molecule is basically kind of satisfied. It's not going to take a second hydrogen ion. And if we speak about this in terms of pKa. Now, do you remember what the pKa is?
pKa, it's the special pH, right?
That's right. So this here, let's say this is our reaction, and let's say there's an equilibrium here, which there is, and let's recognize that K. All right, there's a K for that equilibrium. And then we take the negative log of that K. Can we find that K? How would we find that K?
Is it in the book somewhere?
Yeah, it's probably in the back of the book. They had a nice table for Ks. Let's go find it, okay? So here I am at the table of contents. Let's go into our equilibrium chemistry chapter. All right. And then if we look into the reversible chemical equilibrium section here, I think that we'll be able to find it. I don't see it there. Let's try 6.4. So let's go back into equilibrium, or equilibrium. Let's try this 6,4 here.
Can you look it up online?
Yeah, you can look it up online too, but I just want to show you our reference that we have to it as well. So there's probably a different way to get to the appendixes as well. But here it is, Appendix 11. Appendix 11 gives us a list of all of our acids. And so what we're going to look for here is the carbonic acid. Carbonic acid. So H2CO3, and then we have these Kas associated with this thing acting as an acid. If H2CO3 acts as an acid, what is the chemical equation for H2CO3 acting as an acid?
I guess H2CO3, and then you're going to release a proton, and it's going to have HCO3 minus.
Very good. So that is the first pKa listed on this table, right? Which this K then, for the reaction that we just drew, has a pK or a Ka of 4.5 times 10 to the minus 7. Okay, the K for that reaction is 4.5 times 10 to the minus 7. All right, now, what is the other one that they give us? 4.69 times 10 to the minus 11.
That must be the second one.
That's right. That's this HCO3 minus losing another proton to form CO3 2 minus. And the K for this reaction is the 4.69 times 10 to the minus 11. All right. Now I'm also going to write these in terms of pKa. The pKa here is 6.352, and this one is 10.329. These are our pKas. So what does that tell us? What do those pKa values mean? Do you remember?
At that, there's a special pH, right?
That's right. It's a special pH. And what?
At that pH, you have exactly half of the acid and its dissociated conjugate base.
That's right. Very good. So at pH 6.352, you have half this species and half that species. All right. If I have a solution of carbonate ion in solution at this pH, then this is what's going to exist, half of each of those. If I adjust the pH to 10.329 by adding base, right, getting the solution more basic, then this is the dissociation, or this is the, I'm going to have 50% that and 50% that. Okay? So this also, 10.329, also gives us an idea of what the pH will be when we add something like sodium carbonate into solution. Because when I add sodium carbonate into water, the first thing that happens is, and right away, the sodium ions, to completely separate, and I have basically the CO3 2 minus species in solution. All right. And so right as soon as that happens, this reaction here, the reverse reaction of this, is going to try to occur. The CO3 2 minus is going to try to pull hydrogens. Where's it going to get the hydrogens?
From water.
That's right. It's going to try to pull hydrogens from the water molecules and going to form HCO3 minus and the hydroxide ion. So you put sodium carbonate into water and the hydroxide ion results, making sodium carbonate a what?
A base.
Very good. And when you put sodium carbonate into water right away, it's not going to automatically take, half of the molecules are not going to convert right away to this HCO3 minus. Okay? Most of them are going to be in this form. Some will go into HCO3 minus, but the resulting pH here will be higher than 10.329. Okay? And now, when you begin to add hydrogen ions to this CO3 2 minus, then gradually, and that's what our titration is, right? We have a solution of sodium carbonate. The sodium is a spectator ion, and so essentially we have the carbonate ion, and we're adding protons, right? And when you add those protons, then they will be taken up as, and the resulting ion will be the bicarbonate ion. All right, so we have the carbonate, we're adding protons, and we get the bicarbonate ion, right? Now, this will occur as long as we add hydrogen ions, and when we reach 10.329, we know we'll be at a point where you have half carbonate and half bicarbonate, all right? Now, that's not the end of this step, right? Because the end of this step would be where all of the carbonate is converted to bicarbonate, right? So, when we're at a situation where half of the carbonate has been converted to bicarbonate, we're halfway to our endpoint for that chemical reaction, for that step, okay? So, let's reorganize ourselves and think about this again, or talk about it again. This time, as we talk about it, we're going to talk about it in terms of pH, right? If we monitor the pH of our reaction as we add H ion, hydrogen ion, acid, HCl, right, to our solution, then initially the pH we said was going to be above 10.36, right? And as we add hydrogen ion, the pH, well, initially won't change much because the CO3, 2 minus, that's in solution, is going to be taken up by the H plus ion, or the H plus ion is going to be taken up by the CO3, 2 minus, and we're going to get the HCO3 minus. So I keep adding hydrogen ion, but it keeps being consumed by the CO3, 2 minus to form the HCO3 minus, and so we don't get a significant pH change, all right? So I add hydrogen ion, but I'm not getting a good pH change. And remember, this is our titration setup here. We have our bicarbonate or carbonate in the water, and we're adding HCl into the carbonate, right? And I'm not getting a significant pH change. Now tell me again, why am I not getting a pH change if I'm adding acid? Why isn't it getting very acidic? It's only changing slightly.
Because the CO3 2 minus is consuming that hydrogen ion.
Okay, very good. Now that will occur, and there will be a slight change, and we'll pass through our pH or our pKa of 10.329. So right here we'll be at 10.329, and when we get to that point, 10.329, that will be a sign that we are halfway done consuming all of our CO3 2 minus, or halfway done converting it all to HCO3 minus. All right? And if that's halfway, then when we get to the point where we convert all of our CO3 2 to H plus, or sorry, to HCO3 minus, then these HCO3 minuses won't take any more protons. They don't want any more protons. They have one. They won't take any more protons until the pH gets closer to that of their pKa. So the pKa for this other step, where HCO3 minus takes a proton here, the pKa for this step is 6.352. 6.352. Now, once all of our carbonate is converted to bicarbonate, the hydrogen ion that we add will not be taken up because there's no carbonate to take it up. And so the pH will drop. The pH will drop as our hydrogen ion increases. And once the hydrogen ion concentration begins to build, after a certain concentration, this HCO3 minus ion, which has an affinity, right? Let's draw it again. It does have a negative charge, so it does have an affinity for H pluses, but it's not as strong as the CO3 2 minus because it only has one minus charge. But once the hydrogen ion builds up high enough, then it will be convinced to take a second hydrogen. So once the pH reaches a certain amount, once the hydrogen ion concentration increases enough, then you'll get the pH curve here will level off as your hydrogen ion concentration won't continue to build because these bicarbonates will begin to be converted to carbonic acid, taking a second hydrogen ion. All right? And this will occur, and as this occurs, the pH then won't change much because changing pH means adding hydrogen ion, but as we add the hydrogen ion, what's happening to it?
The bicarbonate's taking it?
That's right, the bicarbonate's now taking it, and so we did get a slight change in, or not a slight, a significant change in pH, but as soon as the hydrogen ion concentration was enough that it convinced the bicarbonate ion to take a second proton, then all the next protons are going to be consumed. And once we're halfway done consuming all of our bicarbonate ion, we're going to pass through the pKa for this equilibrium here of HCO3 minus taking a proton to form H2CO3, which is 6.352. 6.352. That's the second pKa. So this is the first pKa here, and here's our second pKa. Now, tell me again, what is the pKa?
It's a special pH.
That's right. What is its characteristics?
It's the pH where half of the material is associated and half of it is dissociated.
Okay. So for this, what are our two species?
You have the HCO3 minus and the H2CO3.
Very good. So at this point, half is HCO3 minus and half is H2CO3.
Yeah.
Okay. Now this will continue. So, and again, if this is our first endpoint for the first part of the reaction, this from here to here is the first half of our second part of the reaction. And so this distance from there to there will be matched on this side until we get to the end of our reaction. Okay? And that is our second endpoint for the reaction. So this first curve, which is represented by this section, this is our CO3 2 minus taking a proton and forming HCO3 minus. This second section right here, right, from here to here, what's going on there?
HCO3 minus is taking a proton.
And what are the products?
H2CO3.
Very good. Excellent. So this occurs in two steps, right? We, from 105 and 106, we just kind of write it like this, but if we're performing it as a titration, it occurs in two steps. And these are the two steps, right? And if you add these two steps together, you'd get the net ionic equation for this whole reaction as we've written it, all right? And in Chem 105 lab, what we did was we had our two indicators. We had our methyl orange and our phenolphthalein. And the methyl orange, it has a structure. Let's look at the chemical structure of methyl orange. So here's the chemical structure of methyl orange. For those of you who have had organic chemistry, it'll be a little bit more helpful. But each one of these little bonds right here is a carbon, right? These are double bonds. And you said you took organic chemistry, but just for a couple weeks, then you changed classes?
Yeah.
So you probably didn't get to talk about extended pi bond conjugation, right? Because at each of these double bonds, you have a free p orbital. Do you remember that?
Did we talk about that in Chem 105 a little bit too?
Yeah, we talked about that at the end of Chem 105 in Chapter 9 or 10, where there's free p orbitals double bonds, and that's why they don't rotate, right?
Yeah, the p orbitals bond together.
Very good. Well, everywhere where there's an end to a double bond, there is a free p orbital. You see that?
Yeah.
And see how here there's one, 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 here. And there is for sure even one on that sulfur, and there's one on that nitrogen. So we have an extended conjugation system, conjugated system we call this, okay? This ring right here is called aromatic. This one is also an aromatic system. And this extended pi bonds allows electrons to move around, and it also increases the flexibility at which the wavelengths that this molecule can absorb. Now, if a molecule absorbs visible light, then what does that make it?
Is it visible? We can see it?
That's right. If it absorbs a visible light, then it's going to give us a color. We're going to see the distinction by the other colors that aren't absorbed are going to be augmented, and it's not going to look colorless to us. It's going to have a color. And so when you put an extra proton onto this molecule, it goes right here, all right, and it results in a positive charge there, and that positive charge changes this nitrogen and allows it to have extra electron density. And so see how all the electrons can shift in this molecule. See how all those electrons shift? Oh, I'm sorry, the hydrogen's not going onto this nitrogen here, it's going onto this one right here. There it is. And that changes our conjugation. Now we have an extended conjugation starting from here all the way down to here, but then it's broken, or it's changed right about here. And so you get a color change, All right? Now, the affinity for this, or the pKa for this corresponds, and that's why we chose it, corresponds with this, the pH change of about, right here, about transitioning from 5 to about 3. So the pKa for this, let's bring it back up here, for this hydrogen coming off of this proton, or off this nitrogen, is between 4 and 5. So what does that mean?
I'm not quite sure.
Well, that means if the pKa for this is, let's say, 4.5, then at pH 4.5, what happens?
You have half of the stuff on the left and half of the stuff on the right.
Very good. And at pH 4.3, or 4.4, sorry, we're just a little bit below the pKa, what happens?
Well, then the product predominates.
That's right, the product predominates. Mostly this stuff now. And you start off with half at the pKa, but then 1 pH magnitude later, you have 10 times as much of this as you do of that. Okay? So, we chose methyl orange because it changes color. It has a pKa right about the endpoint of this reaction. We also chose indigo carmine, sorry, not indigo carmine, but phenolphthalein, which is our other indicator, because it has a pKa that corresponds with this endpoint. So we didn't have a plot of the pH versus hydrogen ion concentration that we added in our Chem 105 lab. However, we did have the indicators to tell us when the reaction steps had finished. All right, and we used the phenolphthalein, which turned colorless to a bright pink. No, sorry, bright pink to colorless. Turned bright pink to colorless at this transition right here. And then we had the methyl orange that would change color at this transition. Okay? So, titrations are valuable for a couple reasons. One reason is because understanding what's going on at the molecular level gives us good patterns and models for understanding all chemical reactions. So discussing titrations in depth like this is very valuable. Secondly, the value of the ability to perform a titration in an analytical chemistry setting is very valuable as well. It can never be underestimated. There's lots of different instrumentation out there, but when you can set up a quick titration to just answer a question, it's very valuable. Okay? And titrations are not limited to acid-base. There's all sorts of different kinds of titrations, and we'll talk about some of those, but mostly you'll see those, you can read about them in the book. Okay, so let's go back to our book here. And now we're going to go through these chapters, and we're not going to delve deeply into most of this material, but it is a good reference for you so you can have it to try to understand what's going on in titration, so when you need to. But we're going to try to pick out the important vocabulary to start off with and some important ideas. So the titrant is our chemical in our buret that we're adding to our titrand, all right? So our titrant is what we're adding, and our titrand is what's being titrated. You also hear people just calling the titrant the analyte, again, referencing what we're trying to identify. So the titrant and the analyte is also a fine set of vocabulary to be familiar with. The equivalence point is the official point at which your amount of titrant and titrand or analyte is equal. All right. So let's say I have a reaction where I'm monitoring pH, and I have an acid, and I'm adding, let's see, this is HX, and I'm adding base, and I'm going to form water and leave behind the anion there, right? If I start with this acid, pH will be low, and I add base. Again, as I add the base, the pH won't change much initially because the hydrogen ion in the acid is going to consume that base. All right, but as soon as this runs out, then my pH will change drastically. Okay, so here, this is our equivalence point. Equivalence point. And if you're using an indicator, then the indicator might change color right here, or it might change color right here. And so sometimes the equivalence point and the endpoint are different. If you have the ability to plot pH in a titration curve or an acid-base titration curve, then the equivalence point and the endpoint are the same. All right. Equivalence point essentially means the point at which the concentration of your titrant and your analyte are the same, right? Equal concentrations. So you've consumed all of your analyte with your titrant. This here is kind of called the midpoint, right? And at that point, halfway through, you haven't consumed all of your acid, but you have consumed half of it, right? So that point right there is that pH at that point is the pKa for this acid, the pKa for that acid. Okay? Does that make sense?
Yeah, because halfway, half of the HX is now X minus, so half is associated and half is dissociated.
That's right. The midpoint there. Very good. Okay, so let's get back to our book here. In your titration reactions, you need to have some way to indicate that the reaction has come to completion. All right. Now, this titration indication can be a change in a pH curve, a change in a color of a dye, right? You can even do where you look at the temperature of the reaction. So for example, if when you combine X with Y, or sorry, not X with Y, but in this case, well, let's do a more general example of a titration. So if I have X combining with Y, and this process has heat as a product, right? When we say heat as a product, what are we alluding to?
Negative delta H.
That's right, negative delta H. So if X and Y releases heat, and you start with X, and you add Y, right? Then as you add X and combine X and Y, the temperature increases as the heat is transferred, right? Or sorry, as the heat is released. And once all of your X is consumed, then heat will stop being released, and the temperature change will not continue. And so you can get this sort of a curve based on temperature, and you can identify your equivalence point. Now, in reality, the curve will not be so nicely shaped. It would probably look something like this. Okay? And so then you'd say, well, that's not going to be a very good thing. And it has its drawbacks, surely. So this is as I'm adding Y, and I'm monitoring the temperature. However, from these points right here, you can get a nice straight line, which you could fit to these first points, right? And that tells you the rate of change in temperature that you should expect. These points right here are essentially not from the reaction, it's just having excess Y. And so you can plot these points as well and extrapolate a line that way. And this will be a very good indicator of the amount of Y, right? And then from that, you're going to be able to determine the amount of X that you had there. Okay. And this isn't just true for this sort of temperature kind of curve. You can do the same thing with conductivity, for example. You can monitor the change in conductivity. Let's talk a little bit about a conductivity titration, conductivity titration. So if I'm going to have a chemical reaction in which I take sodium chloride and I add silver nitrate, or let's see, silver nitrate. Okay. Actually, let's try to add, instead of sodium nitrate, let's do calcium chloride. Okay. So if I have a solution of silver nitrate, I have a solution of silver nitrate here. And in my Buret here, what am I going to have?
Well, your other stuff, calcium chloride.
That's right, calcium chloride. Okay? And if I monitor conductivity of a solution. Now, what is conductivity of a solution related to?
I'm not quite sure.
Well, it's the number of ions in solution, right?
Oh, yeah, the number of ions in solution.
And not just the number of ions, but the kinds of ions in solution. Okay? And when we say kinds of ions, well, certain ions contribute more in terms of activity to the conductivity of a solution. All right, do you remember our activity table that we talked about not too long ago?
Yeah, I remember the activity table.
Okay, so the activity, if I had a solution, same concentration of silver nitrate and a second solution of calcium chloride, their conductivity would be different. And you can measure the conductivity with a conductivity probe, right? So essentially what the conductivity probe is going to tell you is it has two electrodes on either side of the probe, and it's measuring how easy it is, what kind of voltage you have to apply to get a current across there, or it applies a constant voltage and it tells you how much current jumps across, right? Because based on conductivity, you can get different amount of current transferring across the solution. So silver nitrate, let's remind ourselves what silver nitrate looks like in solution, right? It's really like that, silver ions and nitrate ions. But calcium chloride in solution looks like this, Ca plus 2 and 2 chloride ions. So which one would be more conductive? A solution of calcium chloride or a solution of silver nitrate?
Wouldn't they be the same, or do we have to look at the activities?
Well, here we see that there's 3 ions for every...
Oh, yeah, I see that. 3 ions for every calcium chloride, so that's going to be more conductive than 2 ions for silver nitrate.
Very good. So as I add calcium chloride, then the silver and the chloride ion combine together, and I get AgCl solid, and the result, and also I get calcium ion and plus 2 ion and the nitrate ion, right?
Yeah. So you have to get, well, this isn't balanced.
It's not balanced, but I could do that to balance it, but the reaction isn't going to necessarily occur all at once, right? So we don't need to necessarily think about it in terms of adding 2 moles of silver nitrate to 1 mole of calcium chloride all at once, right? We're gradually adding the calcium chloride. So as we gradually add the calcium chloride, all of our chloride ions are going to be gone, and all we're going to have left is the calcium ion and the nitrate ions, right? And so if we think about it in terms of just 1 drop at a time, right? And so your conductivity is going to change. Your conductivity is going to change. The conductivity of a chloride ion is going to be slightly different than the conductivity of a nitrate ion. And because you're forming a precipitate here, you would expect that your conductivity would probably be either staying the same or going slightly down as this reaction occurred. And so if you monitored conductivity versus the amount of calcium chloride that you add, the conductivity change would probably be something like that. You're adding chloride ion, but the conductivity doesn't change because the chloride ion is being taken up by the silver ion. But as soon as you run out of silver nitrate, how would you expect the conductivity to change?
I guess it would start getting more conductive because you're just adding more calcium chloride.
That's right. So as you're adding more calcium chloride, you would get a change in conductivity. And again, the reality of the curve is it would look something like this probably. Right? But you could take these first points, plot them, take these points here, and extrapolate them like that and find a good endpoint that way. Does that make sense?
Yeah, okay.
And this point here would be what would we be looking for here?
I guess you're wanting to know how much calcium chloride it took to consume all the silver nitrate?
That's right. Again, looking at the conductivity. So this concentration of calcium chloride here would relate to the amount of silver nitrate that was in solution. And you would use the 2-to-1 ratio there, right?
Yeah.
Okay, very good. So let's look at the Buret just quickly here. Your Buret has what's called a stopcock, and sometimes you can get air in here, and so you want to make sure that you fill up your titrant you fill up your Buret with your titrant, and you can kind of flow it through to make sure there's no air, and then close the stopcock and then refill it with the stuff you just flowed through, right? You don't always need to fill it to 0, right? We hopefully remember in 105 that the change in volume can be identified by looking your final volume minus your initial volume, right? Change in everything is always final minus initial, and that difference will tell you how much you've delivered. Here are some specifications in terms of tolerances on different burets. So it makes a difference. This is an electronic or automated titration system, which is nice. Still overcoming the software can be kind of a challenge, but if you understand your fundamentals and you pay attention to what's going on, you can be the kind of person that can show up in a lab with one of these things and figure out how to use it, which extremely valuable skill. Okay, so let's talk about precipitation titrations here. Let's see, where are we at? 8.4, right? Or 9.1. Okay, so we talked a little bit about acid-base titrations already. Let's look at some of these titration curves, right? What's being titrated here?
What's the analyte, you mean?
Yeah, is the analyte acid or base?
We start with a low pH, so we must be acid.
That's right. And as we add more base here, the pH increases, right? Now, if you have a strong acid and you're titrating with a strong base, this is the kind of curve you would expect. Okay? This here is our what?
That's the endpoint.
Also known as the equivalence point. And then this way here would be what?
The halfway point.
That's right. And what's significant about the pH right here?
That means that pH is the pKa for that acid.
That's right, the pKa for that acid. Here, before we start, the amount of our acid is 100% of the acid is still around. But as we begin to add base, we consume it, right, until we get halfway. And at this point, 50% of our acid is left. And at this point, 0% of our acid is left. And if we keep moving forward, all we're doing is just adding base to solution. Does that make sense?
Yeah, that makes sense.
All right. So if we titrate, that's a strong acid with a strong base. If we titrate a weak acid with a weak base, then a couple things different occur. First of all, we generally won't be starting with such a low pH, but that's not necessarily always the case because you can start with a relatively low concentration of strong acid. So that's concentration dependent. But in general, the pH will be a little bit higher. Secondly, you're going to have always going to have a different midway point, halfway point, right? Because the pKa for different acids is different, right? So that's always going to change. In fact, this is a way to identify what acid you have, right? And this has been something that I've used frequently throughout my career to find out what acid is there, what acid is changing the pH, or what species is there, right? Because we think of chemicals as acids or bases, but all chemicals to some degree interact and can change in the presence of hydrogen ions, meaning they can accept hydrogen ions. Or if you add base, then eventually one hydrogen ion will be given to the base, right? So finding out what that pKa is very valuable in identifying what a given chemical is. And ultimately, they're quantitative as well because this concentration here tells you how much you had. Okay? So, when you're titrating a weak acid with a strong base, the pKa is going to be different, right? It's always going to be different. Even if it's two strong acids, it's always going to be different. But then also, the equivalence point here, the equivalence point, the endpoint, is not going to be at pH 7. All right? Everybody thinks that a titration curve passes through pH 7, and it does, the curve will pass through pH 7, but the endpoint won't be at pH 7 if you're titrating a weak acid, okay? And this is why. Let's look at why that's the case. Again, as far as a titration curve is, if you start off with a weak acid and you get, oh, that's a bad drawing. And you get something like that, where we're monitoring pH as we add hydroxide ion, right? Then we start off here with all of our acid, 100%. So I'm going to say 100% at this point is HA. Now this is a weak acid, but it doesn't matter what acid it's some generic acid. Okay? At this point, what concentration of HA do we have?
It's all gone, 0%.
That's right, 0% HA. And halfway in between here, right about there then, what's our percentage HA?
It's 50%.
That's right, 50% HA. Now, if 100% is HA here, HA is there, and 50% HA is there, what happened to the other 50%?
It took, the base took it. The base took the proton.
That's right, the hydroxide ion took the proton away, but we have the other 50% is in the form of the dissociated anion.
Oh, yeah, right.
Very good. And here, what percentage is in the A minus form?
100%.
That's right, 100% here is in the dissociated form. Okay? Well, if that is the dissociated form, A minus, and this was a weak acid, right? That makes this the conjugate base of a weak acid. Conjugate base of a weak acid. And conjugate bases of weak acids are fairly good bases, right? We just saw that the carbonate ion was a pretty strong base. It brought the pH way down to, about 11.5. Okay? So, at this point, at the end point, there's no more HA, but you have a bunch of A minus in solution. And because that's there, it's going to be interacting with any water that it can find and creating a concentration of hydroxide ion. All right? So if this is a weak acid, I know that this point is definitely going to be above 7. So 7 will be below the end point for a titration of a weak acid. Now, why is that again?
Because if you've just titrated a weak acid, then you have the conjugate base of it there, and that's going to change the pH.
That's right. Very good. In fact, if I know exactly where the endpoint is, I can tell you what the pH will be if I know the acid, because I can say this is here, this is the KB, right? This is the conjugate base of this acid acting as a base. So if this here is the pKa for the acid, right? Now there is this relationship here as well. pKa plus pKb is equal 14, just like Ka, big K, A, times Kb equals 14, right? And remember we talked about, oh no, sorry, not 14, but 1 times 10 to the negative 14, all right? Remember how we talked about the log of two things that are multiplied together is adding them together, and pK is just the negative log. So this is the negative log of this, the negative log of this, and so the negative log of that, right? So we have this relationship here, pKa and pKb. So if I know what the Ka is here, then I know what the pKb will be, okay? And now this is not going to be what pKb is. This is not going to be the pH of pKb. But because I know what the pKa is, I can find out what the pKb is. And from this and my equation here, I can create an ice table, right? And I have to know what the concentration here is. So let's say this ended up being 0.1 molar OH minus. That means I had 0.1 molar H plus. And that means also at this point I have 0.1 molar A minus. So that the ice table is created for this, A minus plus H2O, HA plus OH minus. My initial my concentration here is 0.1 now. And I can say it, I'm just trying to find out what the pH is so I can count those as 0. Change, I'm going to lose some to this dissociation. x, gain some, right? Equilibrium, 0.1 minus x, but I don't have to take that minus x into account because it's going to be a relatively small value. So then I can say that x squared over 0.1 will equal the Kb for this reaction, right? The Kb, whatever that Kb is, and then I can solve for x, and that x will be the concentration of the hydroxide ion. Negative log of it would be the POH, and then 14 minus that would be the pH. So based on the concentration, based on the Ka information, right? I know the Ka, I know the concentration here, and therefore I can predict what that pH will be, okay, using this ice table. Okay, so a lot of different things that you can do with looking if you have a nice titration curve provided. Okay. Let's see here. So we can have multiple endpoints. Well, let's look at this first here. This is nice. You see weak acid, strong base titration, where we are changing the amount of, we're changing the same concentration, but we're changing the Ka values for the acids. So here's acid A, same concentration, they're all ending at the same point, but the Ka value, or the pKa for A, which is going to be halfway between the beginning and the end point, is way down here at 1.5 about. But as you change the kind of acid, then you get the pKb, the pKa being at different locations. And sometimes if the pKa is too close to that of your titrant, you're not going to be able to determine the concentration of your acid. See, this F here, you would see this slope like that, and there's no really good inflection point. Even E will be difficult to get the correct inflection point. D, you can see that there's plenty of space where it's changing rapidly, and that's how you identify the titration, the end point of the titration, is you monitor the rate at which this curve changes. So if it starts off flat and then you starts going up sharp, that sharp change there is what you use to measure the end point of your reaction. Okay, so this plot here has two endpoints. What do you think that means?
Well, let's see. Malic acid, pKa 6.3. So it looks like it's a diprotic acid with being titrated with a strong base.
That's right. So this malic acid loses a proton at pKa of 1.91, which is right in here, and then its second proton, the pKa for its second proton is 6.33. All right, very good. And you can see how malic acid and malonic acid change the Ka of the pKa of these protons. And so here's succinic acid, 2 pKa's as well, but these pKa's are getting too close together to distinguish. Can you see that?
Yeah.
And even for malonic acid, this little increase in rate right there is what you'd have to kind of tease out, try to find out exactly where the pKa for the first one is and where the pKa for the second one is. And it might be a little difficult. Okay? So if you want to use an indicator, a color change indicator, the color change that you choose should correspond to the pKa of your indicator. So if I knew that, for example, I was going to be titrating malic acid here. And let's say I wanted to find out when the first proton came off. Then I'd want to choose a pKa that had a similar to this endpoint right here. Sorry, not to this one. Similar to the endpoint. So if my endpoint was going to be around 4, I would want to choose an indicator that had a pKa of about 4, something like this is 3.1 to 4.4, this is 3 to 5. So either something like methyl orange or Congo red. All right. If I wanted to know information about this second pKa here, that's in between about 8 and 10. And here we got 9.6, our phenolphthalein. So it turns out to be the same two that we chose before, right? But the idea is using this kind of a table, if you find the pKa that corresponds to the pH at the endpoint. All right. So to do this, you would have to have known a little bit of information about your titration curve initially, or about your material that you're using, right? Okay, very good. And you have to be careful with some indicators, but the way that I can identify exactly where our endpoint is something we want to talk about here. What we do is we take the derivative, or we look at the change in the in a pH curve here, we look at the change in our y-axis versus the change in x, or we're monitoring the slope at each point as we proceed. So I take my first point and my second point, and I basically identify what the slope is for those 2 points. Do you remember how to find the slope between 2 lines? Or between 2 points, the slope that exists between 2 points?
I don't remember really, but I'll bet I could figure it out.
Okay, yeah, I bet you could. And essentially all you're doing is you're looking at the change in the rise over the change in the run, because the slope is rise over run, change in y over change in x. And so in Excel, if you have titration data like this, you can look at the instantaneous slope, which we also call the derivative. Do you remember that? Did you ever have a class calculus?
Yeah, I did. I took calculus, so I remember talking about the derivative. It's the slope at any point.
That's right. And so we're really using 2 points to get the slope, but we take the instantaneous slope, or the derivative, for all along this line, and this is what our derivative line would look like. It would be pretty low going here. It would be changing a little bit, but on this sort of a scale, this change here would be so much steeper that you wouldn't be able to notice the change along the bottom here. And then as you begin to decrease your slope change, right, you would see this sort of peak if you plotted, again, the derivative versus the volume of sodium hydroxide added. So that peak there helps you identify where the endpoint in our titration is. All right? And if you want to get even more precise, you can take the derivative of this curve, and that is the second derivative here. And what it does is it's not going to change much at all until you get to this point, and then because it goes up really fast, the derivative goes up here, but then it comes down really fast, and the derivative comes down very fast, and then it stabilizes again. So then you have a very specific point where it crosses 0. And so this point right up here, which one is the peak, might be a little bit difficult to see, but where it crosses 0 here, you can solve for that value, and that can give you a very accurate reading. All right? So we're going to work on that. We're going to look at a curve, and we're going to take the first derivative. We probably won't go and take the second derivative, but we're going to look at this and learn how to do that in Excel. Okay? And you did that in 106, I believe. So, but some of you might not have taken 106 yet. All right. So, again, titration curves don't always have to depend on pH, right? Because titrations are not just acid-base reactions. There's lots of different reactions. that can occur. And all you really need to do is set up a way to monitor a change that relates to the endpoint of a chemical reaction. Okay.